there because it's yellow, and this was the Earth orbiting it. Kepler showed that planets orbit in ellipses, right? And that's fine and dandy. But Kepler didn't know why they orbited. Kepler just knew that they did. Why do planets orbit the sun? Why do they do that? Why not just travel in a straight line and not orbit anything? Newton came up with that. Of course, we know now that it's gravity. But Newton figured out that gravity was happening in the sky with celestial bodies. And that was actually a big discovery. You might think now, of course, there's gravity pulling things into the Earth like the moon. But nobody had thought of that before Newton. So that's a big discovery. He came up with calculus. Imagine, those of you who take calculus, it's hard to learn and all that. He invented the thing. The study of curved motion and acceleration and area under a curve and things like that. He came up with how to do the mathematics to do that. And he did it when he was young, like 22 years old. Just a little bit older than you guys. He came up with calculus. Imagine doing that on your own. He came up with gravity and the equations that work with that. He came up with calculus. He came up with Newton's laws of motion. He did a ton of stuff. And so a lot of people think he may have been the smartest guy that ever lived. He was certainly impressive. And he kind of, until Einstein came along, Newton's laws pretty much explained the motion of everything. But Einstein figured out that Newton's laws don't work very well when you start going at speeds near the speed of light. Newton's laws have to be changed a little bit to take very fast speeds into account. That's where Einstein came in and modified Newton's laws a bit. But for normal speeds and normal things we see in everyday life, and for large bodies, Newton's laws of motion work, and work really well. So let's look at some of Newton's laws of motion, and then we'll talk about how they apply to astronomy. Okay? Are we good? Are you excited about Newton?
Yeah. Newton.
We should bring fig Newtons to eat when we're talking about Newton's laws.
So good.
I'll do that next year. Okay, first of all, Newton's first law. An object at rest tends to stay at rest. An object in motion tends to stay in motion. Have y'all ever heard that? That's Newton's first law. You should memorize it, know it. It'll treat you, if you've memorized Newton's laws, you'll do better in science your whole way through college. Okay? So it's good to know these. So an object at rest tends to stay at rest. So here's the guy in a car, an object in motion tends to stay in motion. So a guy driving along in a car, he's in motion, and if he slams on brakes, he'll keep moving forward because an object in motion tends to stay in motion. That's what Newton said. Things want to continue on the movement that they are on, and that's why the guy keeps going forward even though the car has stopped, and he has to be stopped by his seatbelt here before he hits the steering wheel there, and we call this tendency to keep moving in the direction you're going, we call that inertia. People never understood that at first. Newton, people said, no, that's not right. When Newton came up with this, people said, no, things want to be at rest. Things don't want to stay in motion. Everything wants to be at rest. If I take this marker and I roll it along the floor, it's going to slow down and stop. There, it finally stopped. And everybody sees that happen on Earth and says, obviously, objects don't want to be in motion. All objects want to be at rest. That was the thinking before Newton. But Newton said, no, the reason why this thing stops rolling is because it is acted upon by another force. In other words, the reason that guy stops going forward is because he's acted upon by the seatbelt. And the seatbelt stops him. So what is stopping the marker as it rolls? Does anyone know?
Friction.
Friction is stopping it. Friction stops that thing from rolling. there is a force pushing against the rolling. It's called friction, and you learn about that in physics. The floor has some friction, and we'll slow it down and slow it down, and eventually that's why it stops. How does this apply to objects in space? Well, there's hardly any friction in space. There's not much in outer space to slow down an object. So if it's in motion, like the Earth, it's going to just keep on going unless it's acted upon by another force. And so if you launch, it's pretty cool, if you launch a spacecraft out into space and you shoot it off in some direction, it'll keep going in that direction at virtually the same speed you launched it at forever, unless it hits something or is pulled in by something's gravity. Isn't that cool? So if we want to get a spacecraft to Mars, we launch it up out. It's got to be launched strongly enough to escape the Earth's gravity. Where's my globe?
It's right there.
Yeah.
The globe will just.
Or let's say we want to launch a ship to the moon. So there's the moon over there on that cabinet. Y'all see the moon over there?
Yes.
Sitting on the cabinet. That's about how far the moon is actually away from the Earth. If the Earth were this size, the moon would be about half the size of that globe, that moon globe. But anyway, we just shoot the rocket off from Florida here. That's my rocket sound. And it goes up in space, and after it gets above our atmosphere, the engine's cut off. There's no more gas left. They only put enough gas in that thing to get out of the Earth's atmosphere, and then it just goes toward the moon. And in 2 days it'll reach it, because there's nothing to stop it. Isn't that cool? It's got a little bit of gas left so it can make course corrections. It can shoot a little rocket off to change its direction a little bit. And they got several little side cannons to change their direction. But there's not much left in the acceleration point after it leaves Earth's atmosphere. Isn't that cool? Yes?
How do they get back from the moon to the Earth then?
That is a super question. It flies all the way around and all the way here. And of course they got to lead the moon a little bit because the moon's going to move in those 2 days. So you got to take a good shot, but they do. They can calculate it out, and they can make course corrections if they're a little bit off. But they come around and they come here to the moon. Y'all aren't watching over here, Aubrey. This is incredible. This has happened to several astronauts. So they're shooting to the moon, and here they come, and they get to the moon, and they go in just right so that the gravity of the moon pulls them around.
That's pretty cool.
If they're too close, they'll hit the moon. And if they're too far away, they'll fly right past it. So they got to use the gravity of the moon to get them going around.
But when they
Now, the astronauts that landed on the moon, they got just the right distance from the moon so that they go into orbit around the moon. They keep going close. I'll talk about orbit in just a minute. And then they had enough gas left in the spaceship where once they took a smaller ship down to the surface and then back up from the surface and got on this orbiting ship, and then they had enough gas left on the orbiting ship that they could fire away and leave the orbit of the moon and go back to the Earth. So you know what it took to figure out how to do that? Rocket scientists. Question?
What did they say? They left a ship in the orbit and they took a smaller ship.
Yeah, so the ship that went to the moon had a little smaller ship connected to it. Almost like, you take a huge cruise ship to your destination and then you take a smaller ship to the beach. That's exactly what they did. They took a bigger ship and then a smaller ship went from the orbit of the moon down to the surface and landed on it. And that was the one you see them land in. And then they get off, and Neil Armstrong goes, "Hey, one small step for man, one giant step for mankind." And they pick up some moon rocks, and they get back in their little shuttle, and then they launch back up, and then they intercept the orbiting ship and dock to it, and then they take back off and go to Earth. Yeah.
How did they, if the big ship was orbiting around the moon, how did they get the little ship back to the moon?
The little ship had some gas in it too, so it could launch away from the big ship and then it would have to slow down and then land on the moon and then launch back up and get back on the bigger ship. Isn't that great? That's how they got to the moon. They landed on it 6 different times. Yeah.
How fast do the ships go once they quit using gas? Or they just go right into the
About
tank?
13,000 miles an hour.
So even not using any rockets or gas, it just keeps going that speed?
It'll go that speed forever because there's nothing to slow it down, and that's Newton's first law. Isn't that cool? Now there is a few atoms in space that will slow you down, but not much. You might slow down 1 mile per hour per century or something like that. And if you're going 13,000 miles an hour, then you're going 12,999 100 years later. You're not slowing down much. And I might have that way off. You might slow down 0.1 miles per hour per century. I don't even know. There's not much out there in space. There's not many atoms to slow you down. You want to see video footage?
Thank you.
Educator.com. Get help in general and AP physics with video lessons and tons of examples. Learn everything from mechanics,
That's so cool.
fluids, and thermal physics to electricity.
Ask an astronomer.
Hello.
So how do we get everything up into space? Well, we often hear about a guy named Sir Isaac Newton, and we're going to talk about one of his first laws of motion. He has 3. We mentioned them all in various different parts, but his first law of motion is pretty important. Now, it states that objects at rest will stay at rest, and objects in motion will stay in motion. So what exactly does that mean? Well, I'm going to do a quick little experiment here. We have something called a hero engine, which is full of a little bit of water, and the only way out are through these 2 bent pipes that are sticking out on either side. I'm going to hang this up like so. Now this is now an object at rest. It's just sitting here, it's not doing anything. Now I'm going to fire up my trusty blowtorch, which I always get to use pretty much every day, and I'm going to try to heat the water up that's inside that sphere. Now what happens when you heat water up? Most people will tell you, of course, it's going to boil. And when water boils, it produces steam. Now in this particular case, the steam only has one way to get out, and it's the pipe on either side of our sphere. And we're also going to start to get some motion, which is that our little metal ball here is going to start to spin. And this is exactly what Isaac Newton was talking about. We had an object at rest, it just sat there, it didn't do anything, until an outside force, which in this case is the steam, starts it to spin. Now, according to Newton, this thing would continue to spin pretty much forever until it was acted upon by other outside forces. Now, I'll tell you it's not going to spin forever, and that's because there are forces acting upon it right now. And very simply, we've got friction in the chain, which is rubbing against each other. We have gravity pulling down on it the whole time, and it has to work its way through the oxygen that's around. And eventually it will come to a stop. Now, the really neat thing is, though, if we were out in space right now, and I started that to move out in space, we wouldn't have to worry about gravity, friction, or air resistance. This thing would continue to spin forever until possibly it got bumped into by an astronaut, planet, or some sort of spaceship. So Newton's laws, not only do they work here on Earth, they also prove very well to work out in space. For the HR McMillan Space Center and for the Express.
Cool. That was a cool little experiment. All right, let's go to the second law. You want to do the second law? Yeah. Second law is force equals mass times acceleration. This is physics stuff. And here's a guy with a pretty good setup, I would say. I would take him on my golf team, just seeing the setup. I wouldn't even have to see him swing. Because if he can set up like that, I think he can play. Anyway, he's set up. He's about to hit a golf ball here. The force is what he's going to put into it when he hits it. And he's hitting it with the head of the club, which has a mass to it. What do you think the mass of a head of a golf club is? They're not very heavy. It's like a third of a pound or something like that. They make golf clubs pretty light. So anyway, that mass is going to hit that mass, and bam! When he swings and he hits it, it's going to apply a force to it. And that ball is not very heavy, So that ball is going to accelerate very fast. It's going to go from still to about 100, well, with my swing, about 140 miles an hour, 160 miles an hour, in just half a second. I mean, bam, that's a lot of acceleration. And because of that high acceleration, it's going to go, for me, about 320 yards through the air. Because, you know, I hit it a long way. What's that?
Did you know your
I know my numbers. I have a little machine that'll tell you all your numbers. Tell you your club head speed, and your ball speed, and your distance. You set it right by you when you're hitting balls, and you can read all those numbers. It's pretty incredible. So anyway, what if he swings and he hits a truck instead of a golf ball? What if he hits a truck instead of a golf ball? Will the truck accelerate?
No. If it was in
His
neutral,
arms,
it might.
his arms.
It actually will have some acceleration a little bit, but the truck is so much heavier than the ball that the acceleration will be real small because the mass of the truck is so big. So, if you hit against a little ball, that acceleration is going to be great and the ball is going to go a long way. But if you hit against a big truck, that acceleration is going to be really small and the truck will only move a tiny amount, if any. There'll be some force pushed on it. It'll want to move, but it'll hardly move because of the huge mass. Does that make sense? And so this applies all over the place in astronomy. If you want to move a rocket, let's say we want to get a rocket to the moon, and this is what they had to deal with when they were shooting a rocket off to the moon. What's the best way, if we have some gas in the rocket, what's the best thing we could do for our rocket to get it to the moon faster? We're firing gas off that's going to push the rocket forward, and we only have a certain amount of gas. What can we do to get to the moon faster, according to Newton's second law? 10 points, if you can tell me. How can you make, if I only have a certain amount of fuel, what can I do to my rocket ship to make it get to the moon faster? 10 points, you got to write it down. Can you figure that out?
Yeah.
You want to go with that?
Newton's second law will give you an idea.
Yeah. But
You want to go with that?
yeah, but then wouldn't the force be less?
Yes, pink is correct.
So maybe make it. No, they wouldn't make it bigger.
Okay. I'll give it to you, purple. That's not what I was thinking, but
try
that
what
would
you
probably
think.
work.
I don't know.
Yes, blue is correct.
You want to go with that?
Yes, green got it.
Good job.
Anyone
Yeah,
else?
let's go with it.
Alright, we're coming.
Orange, aren't you glad I didn't say banana?
Very.
Okay, I'll give it to orange. So most of you said make it lighter. Make the craft lighter. It'll go faster if it's lighter. That's what it's all about with spaceships, man. Making that thing light. Have you ever watched the movie The Martian?
No.
You need to watch the movie The Martian. They have to get a spacecraft that this guy stranded on Mars is on.
Oh yeah.
He's got to get on the spacecraft and go intercept with the mothership, but he's got to make the thing lighter in order for this to work. So he starts taking pieces off. It's a great movie. You don't need to see The Martian. You can if you watch The Martian, you can take a quiz on it and get extra credit just for watching that if you want to watch it. So that's force equals mass times acceleration. You can give it more force, which is what you said. You could somehow apply more force. Maybe in addition to, what if in addition to putting fuel in the rocket, they had the rocket already moving when it launches? What if you put your rocket on a plane and get the plane going about 500 miles an hour and then launch your rocket off of it? Wouldn't that be better? Wouldn't you be giving it more speed to start with?
Have they done that?
They've done that. That's how they broke the first plane to ever break the speed of sound was launched from another jet.
Game changer.
And he was in his little jet, and there was a big jet carrying it, and the big jet dropped the little jet, and then the little jet took off. A guy in a missile, basically a guy flying a missile, and with some little wings, and he broke the speed of sound. Chuck Yeager, is that what you said? I think his name was Chuck Yeager.
How do you break the speed of sound?
You go faster than sound. So if I yell, "Hey!" that sound actually traveled through the air about 750 miles an hour, and it reached your ear just a second later. It takes a little time. You can go in a plane faster than that. If you're going faster than 750 miles per hour, you're faster than the speed of sound. There's a cool movie on that. I'll show you that movie. Let's watch this video on this second.
Science in a Minute, presented by NSF GK12 at the University of Cincinnati.
What state was he in?
Sponsored by AAAS.
Like, was he like? He'd be like feeling normal, or would?
Hold on.
For approximately 4.5 billion years. And during that time, the moon has been orbiting the Earth in a choreographed circular dance. What is not so evident is that the Earth and the moon are in a violent game of tug-of-war, each aggressively pulling on each other. The moon's pull is evident in the rise and fall of tides in Earth's oceans. But what dictates this relationship? Through Isaac Newton.
I don't like that. I don't like that video. We're not watching that. What'd you ask?
I forgot.
Charlie?
What was it?
What state was he in or something?
Yeah. Like if you were when he was in that little like jet, was he like? Could he feel that?
I think it was in California. Oh, what state?
Did you have like a headache? I feel like going that fast.
Oh no! It's actually it's real rough, and then when you break the speed of sound, it gets real smooth, because the physics of the way the air moves around you changes. If you shoot a bullet, the bullet's going faster than the speed of sound, and one of the cracks you hear when a gunshot is the bullet breaking the speed of sound. It happens so close to the firing of the shot, though, that it sounds like one thing. Okay, so Newton's third law: for every action in nature, there's an equal and opposite reaction. Have you ever heard that? So here's how you fly a rocket: you shoot, you light up fuel inside the rocket, and you only give the fuel one place to go out. It goes out the back. If fuel is shooting out the back, then there's also going to be a push in the opposite direction that moves the missile along, or that moves the rocket along. So if you push one way, there's also a push in the other direction. Let me show you what I mean. If I take a rolling chair, very simple. If I push in one direction, there'll be an equal push in the other direction. You ready? I push that way, and I'm going that way. How is that? Well, that's Newton's third law. For every action, there's an equal and opposite reaction. So, if you think about the pushing, if I had a fire extinguisher, which you can actually find people doing this online, and I'm sitting in a chair, if I fire the fire extinguisher that way, it's going to push me this way. And I'll go flying this way. Did y'all ever see the movie Gravity?
Yeah.
That's one way that she flew through space. And stopped her. She was moving along through space, and she had to stop herself, I think. So she had a fire extinguisher with her, and she fired it in the opposite direction to slow herself down. Another great movie. Watch Gravity, and that's another one you can get extra credit on if you watch that and come take a quiz on it. So yeah, for every action, there's an equal and opposite reaction. Wait a second. I need to get this so it comes up.
Welcome. The European Space Agency suit ESA. Newton came up with 3 laws of motion, laws that describe how forces and objects relate to each other. Hi Pedro, Alexander.
Oh man.
We can see that
I need to get on
the pushing against
Okay.